So you could actually use the unit circle as one way of defining cosine and sine. So cosine is the x-coordinate of a point on the unit circle. Sine is like the y-coordinate, okay? So then like as an example, when I look at this point here at an angle of pi over 6 radians, the x-coordinate is root 3 over 2. So that means like cosine of the angle pi over 6 is root 3 over 2 then. And then likewise at this point, at this angle, the y-coordinate is 1/2, which means that sine of this angle pi over 6 would be equal to 1/2 then, okay? So in general, the x-coordinate represents cosine and the y-coordinate represents sine on the unit circle, okay? All right. So if you know your unit circle, you can figure out the values of cosine and sine at all of these like special angles, if you will, that you will want to know the values of cosine and sine at each of these like special angles. You can probably get by without having it memorized, but it'll be much more helpful if you do have it memorized, or if you can kind of readily figure it out during your studies in calculus. Okay. All right. So let's try to fill out the rest of the unit circle here. So this angle here, does anyone know what that angle should be? The next angle? In degrees and or radians. Yeah, so the next kind of special angle that you want to know is 120 degrees. Okay. Yeah, so in radians, it happens to be 2 pi over 3 radians. And you can figure out what the x and y coordinates are by exploiting the symmetry of the unit circle. So this guy is kind of directly across from the 60-degree point. Okay. So since it's just kind of reflected across the y-axis, the y coordinates will be the same. Because they're at the same height, so the same y coordinate. But now the x coordinate becomes negative since you're now on the left side. So now it's negative 1/2. Okay. All right, so close. That one would be, I guess this one, well, let's see here, what was that? That would be in the 4th quadrant, because you've got a positive x coordinate and a negative y coordinate, so it actually places you in the 4th quadrant. Okay. Let's see here. Oh, am I recording? Yes. Okay, I am recording. Good. All right. So then this next angle here. So it's the 45-degree angle, but like in the 2nd quadrant now. So yes. Let me see. I can't hear you talking. I can hear everything else. Yeah. Okay. Let's see here. I don't know, Jay. Are you able to hear me now, or can you still not hear me? If not, let's see here. Let's try that. Yeah, so yeah, this next angle here is going to be 135 degrees, or in radians, it would be 3 pi over 4. And again, it's kind of the same coordinates as the 45-degree point. It's just the x becomes negative now since we're on the left. y is still positive since we're on the upper half. Okay. All right, so let's just kind of continue. So this next point, it's at the 150-degree angle. It's going to be 5 pi over 6 radians. And its coordinates are going to be the same as pi over 6, but the x will be negative since we're on the left. Yeah. Okay, and then see here, this is going to be 180 degrees, which is pi radians. And I guess here we can see the x coordinate is -1. Since it's a unit circle, so you know it's a distance 1 from the origin. And then it's on the x-axis, so the y-coordinate is 0. Okay. So you don't necessarily need to remember these like off the top of your head, just like readily like that. Although I guess it would help if you do, but as long as you know the angles in the first quadrant, you can use that knowledge to kind of figure out the rest of these angles in the second quadrant. So for instance, like let's say at this angle, let's say you didn't remember what angle this was. So maybe how could you figure it out without just having to like have it memorized, right? So I guess the idea is this angle, it's supposed to be 30 degrees, but from the negative x-axis. Okay. So therefore you could figure out, I guess in degrees, that's like 150 degrees. Okay. Since you know the total is 180. Okay. And you can use that same logic for radians as well. So we know that this angle here is supposed to be pi over 6 radians. And we know that like altogether, this makes an angle of pi radians. So if you're looking for what this angle would be in radians, it would be the total, which is pi, and then minus this pi over 6. So that's like 6 pi over 6 minus pi over 6, and that gets you the answer of 5 pi over 6 for this angle in radians, okay? So if you don't have these memorized, you can still kind of figure it out, just kind of using the symmetry of the unit circle, doing a little bit of arithmetic as well like this, okay? All right, so then just like if we continue this angle here, so it's 30 degrees from 180. So it's going to be 210 degrees now. Or instead of adding 30 degrees to 180, you can add pi over 6 radians to pi. So pi plus pi over 6 give you 7 pi over 6. Okay? Yeah, right. And then you can get the coordinates again by using symmetry. So it should be the same as this point, except now the y becomes negative since it's in the bottom half. Okay, very good. And then let's just finish it up. So this is 45 degrees from 180. So 180 plus 45 is 225. Okay. All right, oh, yeah, so instead of adding 45 to 180, you can also add pi over 4 to pi. That will give you 5 pi over 4 for the angle in radians. And then the coordinates are the same as this point, except y becomes negative since it's on the bottom half, okay? Okay. So then hopefully if you guys weren't too familiar with the unit circle, maybe now you're getting a sense for how you can figure out the unit circle as long as you know the first quadrant. I guess you probably need to know at least that much though in order to get the rest of it. So this is supposed to be 60 degrees from 180. So 180 plus 60 is 240, or pi plus pi over 3 will give you 4 pi over 3. Right, and then again, the coordinates are the same as this one, but a negative y. Okay. All right. Yeah. Okay. So this is, I guess it's 90 degrees from 180. Should add to be 270. Or adding pi over 2 to pi gives you 3 pi over 2. And then coordinates are 0, negative 1. Okay, yeah. All right, and then, so this will be 30 degrees from 270, so it'll be like 300 degrees. You can add pi over 6 to 3 pi over 2. So make that 9 pi over 6 plus pi over 6. Yeah, okay. So then you can get this is like 5 pi over 3 in radians, okay? All right, and yeah, so here this is where the x will be positive, the y will be negative in the fourth quadrant. So it's the same as this point, just making the y negative. So this is like 45 degrees, so 270 plus 45 puts you at 315. Or you could add pi over 4 to this. All right, and then it will have coordinates root 2 over 2 and minus root 2 over 2. Okay. Right, and then this last one, so if you could add 60 to 270, and that gives you 330. Yep. Yeah, so then you can also add pi over 3 to this. And if you simplify, yeah, it gives you 11 pi over 6 in radians. And then the coordinates are going to be root 3 over 2, but then negative 1/2. Okay. And if we go around full circle, we can also consider this to be like 360 degrees or 2 pi radians. Okay. Oh yeah, that's fine. Yeah, I knew what you were saying, so that's good. Let's see here. Okay. And then I guess regarding these angles, so I was like adding like 30, 45, 60 to 270. But actually, usually when I think about those, at least for me personally, I actually like to think about like subtracting from 2 pi. So if you do like 2 pi minus pi over 6 to get down to kind of go backwards down to here, it will give you 11 pi over 6 and so forth. So there's also different ways of figuring out like the angles, but you just need to know the first quadrant at least. And then if you can think about like maybe like what do you need to maybe like add or subtract from an angle to get to another angle, you can kind of figure out the rest of them going from there. Okay. Okay, good. So again, you don't necessarily need to have this memorized, but it's useful to at least be able to think about it and kind of like derive it, maybe like in a similar way that we did here just now. Okay. All right. All right, and then again, just want to emphasize what's the point of the unit circle? The point that it gives us cosine and sine by looking at the x and the y coordinates. Okay. So a couple of things that we can get from that. So many of you might recall how like each of the trig functions are like positive in some of these quadrants and then negative in some of the other quadrants. So if you ever maybe have trouble remembering how that works, it helps if you recall that x is cosine and y is sine. So for instance, for x to be positive, you'd have to be on the right half of the circle. So you'd be looking at the first or the fourth quadrant. So in these two quadrants, the first and the fourth, cosine is going to be positive. But sine is the y coordinate and y is positive in the upper half. So that means it's in these two quadrants where sine is going to be positive. Okay. So you can keep track of where each of them are positive or negative just by thinking about how they're the x or the y coordinate. Okay. And then I've only talked about sine and cosine right now, but of course there are some other trig functions as well, right? So tangent of theta, what's tangent? How do we get tangent from all of this? Yeah, right, okay. So the rest of the trig functions are defined in terms of cosine and sine. So tangent is sine over cosine. Okay, that's good. And then let's see here. The other ones were cosecant, which was just the reciprocal of sine. Secant was the reciprocal of cosine. And then there's also cotangent, which is the reciprocal of tangent. So then those are the rest of the trig functions. And then, yeah, you can relate them to the x and the y coordinates as well. So for instance, like you could say that tangent is y over x and so forth as well, okay? All right. Okay. Let's see here. So where's my, give me 1 second. Okay. So I guess what I want to do right now is just a little bit of practice on familiarizing ourselves with the trig functions and like their values. Each of these special angles, yes.
Yeah, so I just want, so is the point of the unit circle to figure out the coordinate based on the trig function, or is it to know the trig function based on the coordinate, or the both?
For me, it's knowing the trig functions based off the coordinates. I guess you could, so like if you have the like trig functions and like each of their values at these angles memorized, you could certainly do it backwards and then figure out all the coordinates if you know like your trig functions, right? But for me, I guess what I have in mind personally is using the coordinates of the unit circle to kind of know cosine and sine, and then you can get all the other trig functions once you know cosine and sine as well. Okay.
Okay.
Okay. So I guess for those of you who already had the trig functions memorized, you guys are good, if you will, right? But for those who don't have it memorized, the unit circle, I think, is a very good way of helping you to figure out what the trig functions are equal to at these special angles. Okay. So let's just do a couple of like exercises or examples right now. So for instance, when you're working on problems, expressions like maybe sine of 7 pi over 6 might come up. And you're basically just going to need to know what the value of sine of 7 pi over 6 is. So who can tell me what the value is? Okay, yeah, all right, so it's negative 1/2. That is correct. Okay. So if you are looking at a unit circle, you could look at the angle of 7 pi over 6, and then sine is the y-coordinate, and the y-coordinate was negative 1/2, okay? So I'm just going to do a couple more kind of quick problems like this. So, you're working on a calculus problem, and at some point when you're doing your work, you find that you need to evaluate cosine of 5 pi over 3. And this is just something that you'll kind of need to know off the top of your head. Who knows what this would be? Cosine of 5 pi over 3. Yeah, so positive 1/2, okay. And then let's check the unit circle. Let's see here, 5 pi over 3 is here. Cosine is the x-coordinate, so positive 1. Let's do maybe one more. Oh. Okay. If we do maybe tangent of 2 pi over 3. Can everyone see my screen? Or is there like something wrong or no? Okay, all right, okay, yeah, cool. All right, cool, and I think someone answered some minus square root of 3. Okay, so let's check that. Okay. So for something like tangent, if you don't remember tangent immediately, what you can do is think of tangent as being sine over cosine, right? Okay, and then you could kind of maybe think about the unit circle if you need to, but you can figure out what sine and cosine at these two values are. The sine of 2 pi over 3, I think that's root 3 over 2. Cosine 2 pi over 3, I think that one is negative 1/2. So then this does simplify to be, negative root 3. So yeah, that seems to check out, okay? All right. So I guess like however you guys end up like memorizing or however you guys learn to think about the trig functions, you'll want to be able to figure out what the values of the various trig functions are at each of those special angles. Those will come up in a lot of your problems that have trig functions in them, and they are going to expect you to actually like evaluate what they are. And really the only way to evaluate what they are is to just kind of know what the answer is, basically, right? So like, sine of 7 pi over 6, we don't necessarily do much work to get the answer negative 1/2. It's just something that you're going to kind of need to know, or you'll need to be able to kind of maybe, think about your unit circle and figure out the answer from that. But you're going to want to know those values of the trig functions at each of the special values in order to evaluate expressions like that. You may also get some like trig equations, so equations involving trig functions. And to solve those equations, it'll also just be based off your knowledge of the trig functions at those special values. So Let's maybe look at a couple of examples of like solving trig equations right now. So I'll start with some simple ones and we'll look at some harder ones in a bit as well. So let's say I have this equation, sine of theta equals root 3 over 2, and we're trying to solve for theta. I guess let's, just for simplicity, let's restructure ourselves to just an angle between 0 and 2 pi. Okay. Okay, so for an equation like this where we're trying to solve for theta, there's not that much work for us to do. We just kind of need to know the answer almost. So maybe who can tell me what the answers are? Yeah, so pi over 3 is one of the angles where sine is equal to root 3 over 2. There's another one. So where else would sine be equal to root 3 over 2? Yeah, 2 pi over 3, right? Okay. Yeah, so pi over 3 is in the first quadrant. 2 pi over 3 is like the 60-degree angle, but like in the second quadrant, if you will. And then sine is positive in both first and second, so you can maybe use that information to figure out the 2 pi over 3 is the other angle that you need. Okay. Maybe just another kind of simple one like this. So if we have the equation like tangent of theta equals -1. Again, just trying to solve for theta. Again, let's keep theta between 0 and 2 pi. So for something like this, again, you'll just kind of need to think about what the answer is. So who can tell me what the answers would be? Okay, so maybe one hint is, here we want tangent to be negative. So if you think about where tangent is negative, tangent is negative in the second and the fourth quadrants. Okay. One way you can figure that out is the idea that tangent is y over x. So for tangent to be negative, the y and the x would have to have opposite sign. So it puts you in the second and the fourth quadrant. So then you know that you need two angles, one in the second quadrant, one in the fourth quadrant. From there, if you're maybe familiar with tangent of pi over 4 being equal to +1, then you can maybe figure out, okay, so the angles you need are the pi over 4 angles, but in the second and the fourth quadrant. So then that gets you like 3 pi over 4, 7 pi over 4. And so yeah, those would be the correct answers. All right, but again, though, it's kind of hard to, with equations like this, it's kind of hard to like do actual work to solve the problem. So these are instances where you kind of almost need to know the answer to be able to answer the problem itself. So, okay, so maybe before I continue with some more examples, you guys have any questions about anything?
Would you just
Yes.
recommend? Would you recommend just memorizing the radians? Because I don't really see another way around that besides taking a lot of time on.
Yeah, so I guess for me, I have the first quadrant memorized pretty much, and I've worked enough as to where I kind of know the rest of it off the top of my head. But I usually do like a quick check, just because like I always want to make sure that I'm like tell a student the right information. So I always do a quick check anyways. So I'll kind of think about like which quadrant am I looking in? The angle that I'm looking for, is it like the 30 or the 45 or the 60? So I think about things like that. So to me, at the very least, you probably want to know like the first quadrant and at least understand how to figure out the rest of it.
Mm-hmm.
And then if you get more experience working through problems involving trig functions, you'll kind of naturally get quicker. So in that sense, it's maybe not as necessary to memorize the whole thing. You will get quicker as you need to like figure out the rest of the circle.
Okay.
And also, I guess if you work with it enough, you might actually start to memorize a lot of it as well. Okay.
Okay. Thank you.
Okay. Yeah. Yeah. So it's I would say it's up to you then ultimately how you want to study. I don't think it's entirely necessary to memorize the whole thing, but if you can, I think it wouldn't hurt to memorize the whole thing either, though. So it's kind of up to you. Like, what do you think works best for you? Just memorizing it, or do you feel comfortable figuring it out as you need it? Okay. Regarding formula charts, I don't believe you get formula charts. I won't say definitively that you don't though, because I guess I'm not 100% certain. It's been a while since we've been in person, so I maybe don't quite recall how things used to be anymore, right? I know physics would usually get formula charts for their exams. I remember for physics they would. I want to say calculus they didn't, is what I'm recalling. But I could be wrong though, okay? Yeah. Okay, so I'm gonna do maybe one more like trig equation, slightly more complicated, before I move on to like the next section, which will be trig identities. But okay, so sometimes you'll get something like this. So here we've been doing like sine of data equals something, or tangent data equals something. But maybe you'll get something like, I don't know, cosine of like 3 data. And then let's just do like equals, let's do maybe equals 1. And again, we want to solve for data. And again, let's just restrict data to 0 to 2 pi, just to keep things kind of simple. Okay. So how would we go about solving an equation like this? Okay, so let's think about where cosine is kind of, yeah. So you maybe kind of treat data, or treat 3 data as like a single quantity first. So like what angles is cosine equal to +1 at? Yeah, so it's equal to +1 at 0. Not at pi, it's going to be -1 at pi. And then, yeah, so it's also equal to 0 or +1 at an angle of 2 pi. Yeah, okay, yeah, all right. So then that means like for cosine of 3 data to be equal to +1, 3 data itself would have to be equal to 0 then. Or 3 data would have to be equal to 2 pi. And so then if you're solving for data, these are all possible values of 3 data. So then to solve for data, you're going to want to divide everything by 3. So 0 over 3, 0, 2 pi over 3. Okay, now as you guys have maybe noticed, I've kind of left room to add a little bit more to each of these lists. So something to kind of make a note of is, I guess here when we were thinking about the angle 3 data, we kind of only thought about the angles between 0 and 2 pi, where cosine is 1. But there's kind of a problem where when we divide by 3 to solve for data, that leaves us open to finding some more possible values of data that are between 0 and 2 pi. So for instance, like, if I continue going around the circle, cosine is also positive 1 at 4 pi. So 3 data could also be equal to 4 pi. And although 4 pi is outside of our interval, but once you divide it by 3, 4 pi over 3 actually ends up in this interval again, right? So when you have something like this, you might want to go around the circle a couple of extra times as needed in order to get all of the right answers. So then here, this would be all the values of data between 0 and 2 pi. That solves this equation. And here it's kind of maybe worth noting, when we were thinking about 3 data, rather than stopping at 2 pi, we had to go all the way out to 6 pi, so that when we divided it by 3, we could get all the values of data that we needed. So maybe one way you can think about it is, why did we have to go all the way out to 6 pi? So 6 pi kind of means that you had to go around the circle once, twice, and then a third time to get to 6 pi, right? So in a sense, you want to go around the circle 3 times for 3 data. And then to solve for data, you divide by 3, and that'll give you all the values between 0 and 2 pi. Okay. All right, so that was like a slightly more complicated trig equation. So just modify slightly with the 3 data instead of just data. Do you guys have any questions about that? Yeah, so reason why we had to keep going around the circle is because if we just went around the circle once, then we would have just stopped at 2 pi over 3 for data. So the issue is that's not all the possible values of data though between 0 and 2 pi. So you want to keep going in order to find like more possible values of data. And so basically, you want to go around the circle 3 times altogether because of the data being multiplied by 3. And then that will sort of ensure that you get all the values of data in like one interval of 2 pi, okay? If your data is multiplied by a number like this, there's a good chance that you'll want to go around the circle more times to make sure you get all the possible values. Yeah. So like, say if this were like cosine of 5 data, we would have wanted to go around the circle 5 times to try to catch everything. Okay. Yeah, that's a good way of saying it, perhaps. So, yes.
If it was a pi, it was multiplied by pi.
Sorry, can you say that again?
Oh, you were saying you have to go around the unit circle 5 times if it was multiplied by 5.
Yeah, yeah. And so my colleague made me give a good way of thinking about it. So if you want data to be between 0 and 2 pi, if you multiply it all by 3, you want to think about 3 data being between 0 and 6 pi then. So that's why you want to go around the circle 3 times to make sure you get everything.
Yeah. But I don't get why multiply by pi. But wouldn't that just be like how are you getting 5 from that?
No, so that was just like a hypothetical, like if instead you had cosine of 5 data. So what I was saying, if instead you have something like that,
Okay, pi.
then you'd have to go around like 5 times, yeah.
I heard pi data, like the symbol pi.
Oh, okay, I see, yeah, okay, that's my bad, yeah.
Yeah, sorry, my bad.
Yeah, no problem, yeah. No, I understand. Sometimes it's hard to catch what someone is saying, especially when you're virtual. All right, so I don't know if you guys have any other questions about anything so far. Okay. I'm going to go on to the next section, which is trig identities. Okay. So you maybe, I don't know how many trig identities you guys recall. There's a couple of trig identities in particular that are good to know for calculus, though. So I'm going to highlight the ones that I think are like most important for the calculus courses. I'll start with the Pythagorean identities. So there's 3 of them, although you can probably get by with just 2 of them, but I'll mention all 3. So the first one, most of you are probably familiar with this one, but it's sine squared plus cosine squared is equal to 1. Does anyone know why that is true? Yeah, so it's actually a consequence of the Pythagorean theorem, that's right, and hence why we call it a Pythagorean identity. But just so you guys can kind of understand why that would be true. So if I draw a picture of the unit circle, let's say I just pick a random angle, radius is 1. So we can create a right triangle, and if we remember that the x-coordinate is cosine, the y-coordinate is sine. Okay. For the right triangle, you can use the Pythagorean theorem, which should tell you that x squared plus y squared equals 1 squared. And that's how you get cosine squared plus sine squared equals 1. Okay. Okay, now, after you get that identity using the Pythagorean theorem, you can get some other identities by kind of manipulating this first one. So if I were to take this first equation and divide everything by cosine squared, so dividing both sides by cosine squared will give us sine over cosine will be tangent. So sine squared over cosine squared will be tangent squared. Here, dividing by cosine squared gives you 1. And then 1 over cosine of secant, so you'd end up with secant squared on this side. Okay. So that's another one of the so-called Pythagorean identities. So again, you can obtain this identity just by taking the first one and dividing everything by cosine squared. Third one is if you divide everything by sine squared, as opposed to dividing everything by cosine squared. So if you divide by sine squared everywhere, you're going to get 1. Cosine over sine is cotangent. And then dividing by sine, you'll get cosecant on this side. Okay. So these are all useful identities to know in calculus. I feel like I don't use the third one much. That's not to say that you won't be using it at all. But I feel like I use the first and the second one a lot more. So if I had to highlight which ones are the most important ones, it would be the first two. But again, it's good to keep in mind the third one still. Okay. So those are some of the identities that you'll want to know. I'll mention a couple other identities, which I think you'll also want to know. So the double angle formulas for sine and cosine come in handy often. So, oops. Okay, I've never seen that before. So the double angle formula for sine says that sine of 2 theta is equal to 2 times sine of theta times cosine of theta. And then for cosine, there's actually a couple different formulas for cosine, but I always have one of them memorized, which is, I remember that cosine of 2 theta is cosine squared theta and minus sine squared theta. Okay. Now, however, you can get a couple other different expressions as well for cosine of 2 theta. So if you use this first Pythagorean identity and combine it with this identity here, you can come up with a couple more expressions for cosine of 2 theta. So as an example, from this Pythagorean theorem, you can see that cosine squared is equal to 1 minus sine squared. So in this identity here, if I replace cosine squared with 1 minus sine squared, so 1 minus sine squared theta minus another sine squared theta gives you 1 minus 2 sine theta. Okay. So that's like another way of expressing cosine of 2 theta as being 1 minus 2 sine squared theta. And then you can get one more formula by, instead of replacing cosine squared with 1 minus sine squared, you can instead replace sine squared with 1 minus cosine squared. So if you do that, here, distributing the minus the cosine squared would add together, so you would get 2 cosine squared theta. And then you still have a minus 1. So that gives you like another formula for cosine of 2 theta. Okay. So I guess all in all, we have 3 different formulas for cosine of 2 theta. All of them are valid, but You can maybe see the difference between each of them though. So, in the first identity involves cosine and sine, but the second formula only involves sine, and the third one only involves cosine. So, in a problem, if you have cosine of 2 data, you might wonder like which of these 3 identities would be best to use in that particular problem. And one way you can figure out which of these 3 you want to use is based off the results. So, do you think it'll be better to replace cosine with only sine, then you'd use this identity? Or if you want to end up with more cosines, you would maybe use this identity. If for some reason it seems convenient to have both cosine and sine up here, you'd want to use this first identity. Okay. The third one I got by taking the first one and replacing sine squared with 1 minus cosine squared. So let's see here. Yeah, so if we replace sine squared with 1 minus cosine squared, it will lead you to that third formula. Okay. All right. So if you remember how we got the second and the third ones, then you can get by, and this is how I do it then. So I just remember the first one. And then I just know that I can get the other 2 by using this Pythagorean identity. Okay. There's one more set of formulas that I think are useful for calculus. Yes, okay. So this third one, let's see here. So I guess for the second one, we get the second one by dividing the first one by cosine squared. So this third one you get from the first one if you divide by sine squared. Okay, all right, cool. All right, and then there's one more set of formulas which I think are useful to know. These are more useful, well, so these are more useful when you get to the integration part of calculus. They're usually called the power reducing formulas. But the power reducing formulas are, so cosine squared of theta is equal to 1 plus cosine of 2 theta over 2. Which sometimes I like to factor the 1/2 out in the front. So sometimes I write it like this as well, but they're both the same. And then there's also one for sine. So sine is the same as cosine, except in the formula it's going to be minus instead of plus. And then again, sometimes I find it convenient to factor the 1/2 to the front. Okay. All right. So the way that I kind of remember these two, so like sine has like a minus, so, and then cosine, so it's like cos kind of has a plus to it. So there's kind of like a weak connection, if you will, in that sense, like sine minus. They don't rhyme, but I don't know what the word is for that thing, but they sound similar, right? So that's kind of how I memorize that.
One question.
Yes.
So the whole point of trig identities are just for our benefit, like when we're trying to reduce an equation, or like let's say we're working with cosines, then like we want the answer to be output it as a cosine, then we would probably use like more this.
Yeah, so yeah, let me try to illustrate with at least one example of like using these identities in order to like actually do something, right? These are the power reducing formulas over here. The reason they're called power reducing is you go from cosine being squared to cosine not being squared. So that the power is going down by 1 when you use the formula, okay? But yeah, so I'll do at least one example using where I use at least one of these identities to like accomplish something, if you will. I've got a couple of examples, but let's just stick with one at least for now. Let me see here. Let's do this equation. Okay. So I think Les will post that. So here, let's look at this equation. Cosine squared theta plus sine theta plus 1 equals 0. And let's say from this equation, we want to solve for theta. Okay. Again, just to keep it simple, let's keep theta between 0 and 2 pi. Okay. So it's this equation. It's a little bit more complicated than the trig equations that we looked at previously. One of the reasons why it's complicated is because this equation involves multiple trig functions. It involves both cosine and sine. So whenever you have an equation like this involving more than one trig function, it's often helpful to use a trig identity to rewrite one of your trig functions in terms of the other one, okay? So for instance, what I would want to do in this equation, or at least what I think would be a good idea, is to use the Pythagorean identity. So if you remember that cosine squared plus sine squared is 1. So we could replace cosine squared with 1 minus sine squared. Oh. Yeah. So if I make this substitution in the equation right now, so replacing cosine squared with 1 minus sine squared. Okay. So now the equation is a little bit simpler now because at least everything is in terms of sine only instead of having both cosine and sine, okay? So let's continue with what we have here now, and let's see what we can do to solve for theta. Okay. I'm going to rewrite the equation a little bit, so let's see here. I'm just going to add the two ones together first. So 1 plus 1 will just simplify to be 2. Okay. Okay, and here this looks kind of complicated, but you can kind of think of this as just like an ordinary quadratic equation. So it's kind of similar to if you had an equation like minus x squared plus x plus 2 equal to 0. So maybe before I continue with this problem, I'll do like a brief kind of side problem here where I'm thinking of how this equation is kind of like just a quadratic, but in terms of sign. So I want to maybe first think about how would I solve this kind of quadratic equation. And so to solve the quadratic, usually what you'll be doing is factoring it. So let's try to factor what we have here right now. I guess personally, the minus in front of the x word bothers me, so maybe what I would do first is just to multiply both sides by -1. It's not necessary, but that's just like a personal preference, if you will, doing that. Okay, yeah, right, okay. And then here, can we factor this quadratic? And if so, who can maybe tell me how it factors? -2 plus 1. Okay, yeah, that's good. Okay. So then that leaves us with x being equal to 2, or x being equal to -1. Okay. All right, but now let's go back to the actual problem. Okay. So what we did, like going from here to here, is we were thinking of sine data as if it were just like one quantity, just one variable x. So when we solve for x down here, and in fact, you can think of it as having solved for sine of data. So when we get x equals 2 or x equals -1, going back to the original problem, that means like, either sine of data should be equal to 2, or sine of data should be equal to -1. And yes, okay. So now that we have these two equations, we have to just kind of use our knowledge of the sine function to figure out what the answers are. This equation, sine data equals 2, has no solution. Why does this have no solution? Who can see why this equation has no solution? Okay, so this equation has no solution because, yeah, okay. Something that's good to know about both sine and cosine is sine and cosine are always going to be between -1 and +1. So that's like the range of the two functions. They can never achieve a value beyond this, oops, beyond this range. That was, well, I guess that was technically, well, okay. Yeah, so because sine data can never go past a value of 1, therefore it's not possible for sine to ever be equal to 2. So hence we say no solution, okay? Okay. As for maybe like, if you weren't familiar with this fact, maybe like one way you can think about it is in terms of the unit circle again. So remember sine and cosine were like the x and y coordinates of a unit circle. But if you think about the unit circle, x and y will never go beyond -1 and 1 in a unit circle. So that's why cosine and sine can never go beyond -1 or 1, okay?
Oh, so question.
Yes.
Yeah, so even if you have a second rotation, like even if you go to 4, 5, the coordinates will be the same. Is what you're trying to do.
Yes, that's correct. Yeah.
Okay. So like, I'm kind of confused like on one thing, which is the so sine theta, like in terms of degrees, it has to be less than 1. That's what you're saying, like -1 to 1.
So I guess yeah. So the value of sine at any angle regardless of that angle being like between 0 and 2 pi or like in any other interval. No matter what the angle is, sine at any angle is always between -1 and 1.
Yeah. Okay. So, how does the actual value of pi relate to the unit circle? Like pi, like 3.145. So that how does that value relate to the unit, to the degree unit? There's no connection.
So pi and all those other like pi numbers, like pi over 2, pi over 4, and so forth, those were like angle measures in radians. So I'll just briefly come back to the unit circle page. So the connection was like, remember the coordinates are the value of cosine and sine, but at a particular angle.
Right.
So like here I mentioned how like, what does all this together tell you? So specifically like cosine at pi over 6 radians, or cosine of pi over 6 radians is √3/2. Now sine evaluated at pi over 6 radians is 1/2. So that's kind of where the pi's come into play. They're referring to like the angle that you're like plugging into your trig functions, if you will. Okay.
Okay.
Okay. Let's see here. And then for this example, when we looked at sine data being equal to -1, there's one possibility between 0 and 2 pi that happens when data is 3 pi over 2. So then this was the only solution that we found then to the equation. Okay. But here, this is just kind of an example of one instance where you might need to use a trig identity. It's when you're solving a trig equation that involves like more than one trig function. You might want to use a trig identity to try to get it all in terms of just one trig function instead. So like just sine as opposed to cosine and sine. Okay. At this point, I would like to take just a short break. So let's take like a short 5-minute break, and then I'll get to the rest of what I had prepared, which is actually not quite as much as the first two. So I think we're still kind of on track because of that. But yeah, so let's take a short 5-minute break or so. So let's come back around 2:20. And then I guess in the meantime, you guys can ask me, whatever questions you may have. So yeah, so going back to where this came from. So that came from the work that we did down here. So we kind of just thought of sine data as being a single variable x. We solved for two possible values for x. And since x is sine, that gave us two possibilities for sine of data. But one of them led to no solution. So this is the only one that gave us an actual answer. Okay. All right. Yeah, the recorded lectures are going to be up in, they're going to be posted to our YouTube channel, which I know someone linked to earlier, but we'll link to it again. Yeah, okay. So I know there were some questions about the different calculus sequences, so maybe I can talk a little bit about that. Okay, so for the applied calculus sequence, so kind of what's the difference between all three of them? So for the applied calculus sequence, the biggest difference is that you don't do anything with trig functions. So if you do math 1325, math 1326, you should never encounter a trig function like in any of your homework problems or any of your quiz or problems or anything like that, okay? So there's no trig whatsoever in the applied calculus sequence. And the other calculus sequence do involve trig. Yeah, everything that I'm talking about today is not going to be important for applied calculus, okay? Although the stuff that we talk about later in the week, so tomorrow, Thursday, Friday, some of that stuff is going to become relevant again for the applied calculus sequence. Okay. They tend to not really review this stuff in your calculus courses. 2413 does kind of a very quick pre-cal review, like the first week, maybe two. They don't necessarily go over what I'm going over right now for trig, but it's kind of a quick pre-cal review before they dive into calculus. If you're doing 2417, 2419 track, you're going to start out with calculus right away. I don't think they do much of a review if you do that track. No, I wouldn't expect them to do a quiz on the first day of class. Yeah. If they were to do something like that, it would probably be like an ungraded assignment, and they're maybe like trying to gauge where everyone's at or something like that. But yeah, I don't think they would do something like that though. Okay. For the other two sequences, so 2413, 2414, 2417, 2419. So this sequence compared to this sequence. So I guess the 2417-19 sequence moves at a faster pace. And it also covers more material. Compared to 2413, 2414. So these are at a much more comfortable pace, I would say. Not necessarily that it's like super easy or whatever though. Roughly speaking, 2417 and 2413 are like Calc 1. And then like the 2419, 2414 are kind of like the Calc 2 of the two sequences. So Calc 2 involves more integration as opposed to differentiation. Although in 2417 you do some integration. Well, I guess both 2417 and 2413 does a little bit of integration at the end of the semester. 17 does more. So I guess generally speaking, 2417, 2419 is more difficult. As opposed to 2413, 2414. Yeah. That's a little bit, yeah. You can maybe think of it as like 2413, 2417 as being more analogous to AB calculus. And then like 2419, 2414 is maybe more like a BC calculus, if we're kind of like relating it to like the sort of the AP calculus. Okay. So like if you have the option between the two sequences, and let's see, so how would I put it? So if you had the option between 2417, 2419 or 2413, 2414, if you're not doing like a math heavy major, so like you're not really expecting to do that much math, you might want to go with 2413, 2414 because it's going to be a little bit easier. Now, I know some people, depending on what your major is, have the option between 1719 or 13, 14, 15. So I think it's maybe like engineering majors might have this option, like these two versus these three. So between like these two options, this sequence covers the most out of like these three options. This triple sequence covers the most. A prerequisite for statistics. Assuming stats is statistics, right? Not really. I don't think so. There might be like a calculus prerequisite for a stats class, but it's probably not super. Your stats class probably won't be super heavy in calculus though, unless you're thinking of like one of the higher level stats courses, which I would assume you're not thinking of just yet. I believe 2413, 2414 is an option for med school or like chemistry or biology. So those kinds of science majors. I think they have the option between 1314 and 1719. So I guess like for those majors, I generally would recommend 1314, unless you feel like you're a very strong math person, in which case you could certainly do 1719 as instead. But if you're not that strong of a math person, you might prefer the 1314 sequence. Okay. So I guess that's maybe just a little bit of the difference between the three of them. I'll go ahead and get back to the trig review though. At the end, if you guys have more questions, I can try to talk a little bit more about each of them. But for now, let's go ahead and get back to the workshop, okay? All right. I mean, I guess most of you are familiar with the SOHCAHTOA thing, right? So it tells you how like the trig functions relate to right triangles. So the SO is sine is opposite over hypotenuse, cosine, and the cosine is adjacent over hypotenuse. TOA, tangent is opposite over adjacent. And then you can figure out the other three. If you just remember, cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. Cotangent is the reciprocal of tangent, right? Okay. So there are instances in calculus where you'll have right triangles in your problems, and you'll need to maybe do a little bit of SOHCAHTOA to help you out in that problem. Let's maybe look at just kind of a small example. Let's say we have a right triangle, which I'm going to draw right now. This angle theta. Let's say we know that this side has a length of 3. And let's say that this side has a length of x. And then based off that information in that right triangle, I want to know maybe like what is sine of theta going to be. So to figure out what sine of theta is going to be, we can use the idea that sine is opposite over hypotenuse. Okay. And then we can look at our right triangle, and we know that the opposite side has a length of 3. The hypotenuse, I don't have it in this picture, but maybe we can figure out what the hypotenuse is, right? So maybe he could tell me what the hypotenuse would be. Hypotenuse, I guess the hypotenuse would be 5 if x were equal to 4. That would be a 3, 4, 5 triangle. But yeah, so we don't know what x is though, but what you can do is use the Pythagorean theorem. Yeah, okay. So remember the Pythagorean theorem says, this is a and that's b, so a squared plus b squared equals c squared. So then c itself would be the square root of a squared plus b squared. Okay. So you want to use the Pythagorean theorem to figure out the hypotenuse. Oh, jeez. Okay. Right. Okay. And then from there, so now we know the hypotenuse has a length of square root of x squared plus 9. And so then that would be the sort of an expression for the sine of theta. Okay. And then of course you can figure out any of the other trig functions as well. So maybe just like one more example, if we look at say secant for this example. So secant can say it's the hypotenuse over the adjacent. It's the reciprocal of cosine. Okay. All right, and then here we know the hypotenuse is square root of x squared plus 9. And the adjacent was x. So secant theta, an expression for it would be square root of x squared plus 9 over x, based off this right triangle that we have. Okay. Let's maybe do one more kind of a small example, kind of similar. So this time, let's say that we're given, let's say we're given a cosine of theta is maybe x over 5. And then let's say we want to find the values of, I don't know, let's do like maybe sine and tangent. Okay. So one way you can kind of think about how to go about figuring out what sine and tangent are is to construct a triangle to kind of help you visualize the problem a bit more. So let's mark this angle as being theta. And then we know that cosine is the adjacent over the hypotenuse. So given that cosine is x over 5, that suggests that we can consider the adjacent side of this triangle to be x, and the hypotenuse would have a length of 5, okay? And then with that information, if we want to figure out, say, sine, yes, yeah, does someone have a question or? Oh, all right. Yeah, so if you have a question, you can post it in the chat. What was I going to say? Oh, right. Okay, so like in this example, we're looking for sine of theta. And we know that sine is like the opposite over the hypotenuse. So then to get sine, we would need to figure out what the opposite side would be. So maybe how could we figure out the opposite side with the information that we have in this picture? Okay, well, so we could use the Pythagorean Theorem for it, which I think is what you guys were doing. Yeah, so we know that x squared plus whatever the opposite side is squared should equal the hypotenuse squared. So then if you minus the x squared over and then square root to solve for the length of the opposite edge, so you will get square root of 25 minus x squared. Okay, very good. Yeah, okay, all right. And then now that we have that, we know sine is opposite over hypotenuse, so here sine would have been square root of 25 minus x squared, all over 5. And then just to finish up the problem, tangent was opposite over adjacent. So then opposite over adjacent for this problem, 25 minus x squared, x. Okay. Okay, so then these types of situations, they often happen when you get to like a trig substitution, which you will get to at the end of 2417 or kind of early in 2414, whichever sequence you are in. And then there are some other types of problems where you'll need to know your SOHCAHTOA to work through that problem. So that's kind of good to keep it in mind. Yeah. Uh-huh.
The two tracks, like the 24, 30, like each one is a semester long, right?
Yeah, each one is a semester long, that's right.
Okay, yeah.
Okay. Okay, so that's I think all I'm going to say about the right triangles. So I guess I'll quickly talk about the graphs of the trig functions. Not going to say too much on it, but I think that's kind of good to have a sense for what the graphs look like. So then here I've gone ahead and included graphs of each of the 6 trig functions. Sometimes if you think about the graph of the function, it can help you in thinking about a problem. So these are kind of good to have a sense for what they look like. Sine and cosine have a little bit of a periodic kind of a wave shape in the graph. Remember, sine starts at the origin, cosine starts at the top because sine is 0 is 0, but cosine is 0 is 1. So you can kind of figure out like where sine and cosine start based off that. Notice that the other trig functions have these vertical asymptotes in all of their graphs. So if you think about, say, like a tangent right now, so you might recall how tangent is sine over cosine. So these vertical asymptotes, the graph of tangent, the vertical asymptotes are going to occur whenever the denominator is 0. Oh, sorry, not horizontal, vertical. And then we know that cosine is 0 when x is at pi over 2 radians, 3 pi over 2. Those are like kind of the two 90-degree angles, if you will. I forgot to mention negative angles. I meant to mention that earlier, but are you guys familiar with the idea of a negative angle? Yeah, so when we were looking at the unit circle earlier, we were always measuring the angle counterclockwise from the positive x-axis, but if you measure an angle clockwise instead, angles that are kind of measured clockwise like this are considered negative. Okay. So in that sense, we're able to allow for negative angles, and that's why we have negative angles or negative values appearing in the domain of each of these trig functions. Okay. Okay, so yeah, it's just kind of good for to see all the graphs. I'm not necessarily going to do much work with this though, but I at least wanted to show you guys a picture of all of them. Okay. Okay. I guess what I want to do though for the rest of the time that I have is start talking about the inverse trig functions. So I'm going to jump to that now. Okay. And so I guess for the inverse trig functions, so here I have a graph of the sine function in particular right now. So what's the idea of the inverse function? So I guess the idea of the inverse function is, given a value in the range of sine, you want to sort of work backwards and figure out what in the domain will be mapped to that value in the range. But sine is a little bit complicated because if you look at a single value in the range, there's multiple like x values that will map to it. So here you can see like in this picture that I have right now, each of these values on the x-axis are going to map to the same value t. Yeah. So if you're trying to look for the inverse function, there's kind of a difficulty because like the sine inverse of t, right now it looks like there's more than one possible value for what it could be. So in order to define the inverse trig functions, you have to kind of put a restriction on each of the functions in order to get like a definite value. So for defining the inverse sine function or arcsine, we put sort of a restriction on the inverse sine function where we restrict the domain of sine to just the interval from negative pi over 2 to pi over 2. And when we make this restriction on the sine function, we can then define the inverse function based off that restriction. Okay. So the idea is if we restrict our attention to just this strip, if you will, So we ignore everything outside of that strip. So now for a value in the range of sine, we can find exactly one value in the domain that corresponds to it. So we'd be ignoring the rest of these possible values because they're outside of the strip. And then because we have a definite value now, that allows us to define the inverse sine function. So how does the inverse sine function work then? So the inverse sine function is basically the value in the domain that I need to plug into sine in order to get well, the corresponding value in its range. So basically, if you're trying to figure out like sine of what angle will give you some value t, that angle that satisfies that equation is sine inverse of t. But we have this restriction though that sine inverse, its range has to be between minus pi over 2 to pi over 2 then. Okay. Whereas the domain of the inverse sine function so then the domain of the inverse function is the range of the original. So the range of sine is from -1 to 1. So the domain of its inverse is -1 to 1. Okay. And if you were to maybe, well, so if you were to look at a graph of the inverse sine function, I also have the graph of that, the rest of them over here. Okay. So basically for the arc sine or the inverse sine function, its domain is from -1 to 1, and its range is specifically from minus pi over 2 to pi over 2. And the reason why that's the case is because of our decision to restrict our attention to that interval in order to define the inverse sine function. Okay. The other inverse trig functions, they have a similar restriction as well. So for the inverse cosine function, we kind of restrict our attention to angles between 0 and pi in order to define that. For inverse tangent, we restrict our attention to angles between minus pi over 2 and pi over 2, and so forth. So all of the inverse trig functions have this kind of restriction in order to define them. I don't use these three much. I mean, like, honestly, I don't think I've ever used any of these three before, but I included them just for completeness. So you have those three there, but I think you'd probably be working with arc sine, arc cosine, arc tangent the most out of the 6 of them. Okay. So then let's maybe spend the rest of the time just kind of looking at some examples involving the inverse trig functions. Okay, all right. Okay, so we'll look at some, oh, geez, okay. All right, so we're going to look at some simple problems, and then we'll look at some more complicated ones at the end. Oh, thank you, no problem. Okay, so let's say that we want to find arcsine of 1/2. Okay, so then, like, how do we go about doing these types of problems? So I guess the way that I think about the inverse trig functions is, okay, so the idea of like arcsine is arcsine of 1/2 returns an angle. And this angle is supposed to satisfy the sine of that angle equals 1/2. Okay, so then we can maybe think about, okay, what values of what angles data will satisfy sine of data equals 1/2. Maybe you guys can help me out here. So for what angles data is sine of data going to be 1/2? Okay, pi over 3, 5 over 6. All right, so quite a few answers there. Let's see here. Sine is equal to 1/2 at an angle of, it's going to be pi over 6 in the first quadrant. Yeah, 5 pi over 6 in the second quadrant. So at least those would be the solutions between 0 and 2 pi. Okay, but arcsine of 1/2 is going to be only one of these values. So maybe which of these angles is the right answer, and why? Yeah, so arcsine of 1/2 is going to be equal to pi over 6 in particular. Okay. And the reason why we choose pi over 6 to be the answer is because of our kind of restriction on sine here. So when we were thinking about the inverse sine function, we were restricting our attention to angles between minus pi over 2 and pi over 2. Okay. So then 5 pi over 6 is not in that interval, and that's why that one was no good. Okay. So then because of that restriction, we kind of know to narrow our attention to just pi over 6, and then that would be the answer to that. Okay. So let's look at some of the other inverse trig functions. I'll do one or two more examples kind of like this. Let's maybe do like arc cosine next. And let's say we want arc cosine of, let's do maybe negative 1/2. Okay. Okay, so in order to think about what this is going to be, so I guess like, again, the way that I usually think about it is, okay, the inverse trig functions, they return an angle. Okay. So arc cosine of negative 1/2, it's an angle theta. This angle theta that I'm looking for needs to satisfy cosine of theta will be negative 1/2. Okay. And then there's a restriction on this angle as well. So We talked about for arcsine, there's this restriction that it has to be between minus pi over 2 and pi over 2. I didn't talk about it, but I kind of mentioned it when I looked at the graph earlier. So for inverse cosine, the restriction on the angle is that it has to be between 0 and pi. Okay. So then just kind of a quick look at that. So again, for arc cosine, the angles are restricted to be between 0 and pi for that. So then we need to think about, what angle satisfies cosine of theta is -1/2. And then we also need it to be between 0 and pi. So let's see here. I guess for cosine to be negative, we're going to want it to be in the second quadrant. And that will put it between pi over 2 and pi in particular. And then as it's got 60 degrees, so yeah, 2 pi over 3. Yeah, so then 2 pi over 3 would be the angle between 0 and pi. It satisfies this equation. So then we could say like arc cosine of -1/2 would be 2 pi over 3 in particular, okay? Okay, so that's good. Yeah, so the restrictions on arcsine and arc cosine, they differ from each other, okay? So for arcsine, the angle that it returns is always between minus pi over 2 and pi over 2. For arc cosine, it's going to be between 0 and pi. You can see for arctangent, it's between minus pi over 2 and pi over 2 again. But this time, minus pi over 2 and pi over 2, though, they are excluded, though, whereas for sine, they are included. Yeah, you can see the kind of the restriction for them here as well. So arc cosecant goes from minus pi over 2 to pi over 2, but 0 is not in the range of it, okay? And then there's similar restrictions for the others as well. So you can kind of look at the range of each of the functions to determine what the restrictions are, okay? Okay. Let me just squeeze in one more example, and then we'll wrap things up for the day with that. Let me see here. Sure. Let's maybe do something like this, and we'll end it with this. Okay, so let's say we had this expression cosine of arcsine of x. Okay. And maybe before that, I guess something that's kind of good to note. So sine and arcsine being like inverses of each other, they kind of cancel each other out in the sense of like sine of arcsine. If you have an expression like this, the sine and the arcsine cancel out, leave you with x. So it's the same as like cosine of arc cosine, they would cancel each other. A tangent of arctangent, they also kind of cancel each other. It's kind of worth noting that they don't cancel if you do it the other way around, though. So like arcsine of sine, that actually doesn't work as nicely, and it's kind of because of the restriction, but when you compose them like that, they actually don't quite cancel. Okay. Okay, but what I want to look at though, just as a final example, so I want to look at something like cosine of arcsine. And maybe there's a question of like, how can we kind of like simplify this, if you will. And there's a couple of different ways of how you can think about it, but what I'm going to do is I'm going to make a right triangle to help me think about this problem. And there's a couple of different ways of how you can think about it, but what I'm going to do is I'm going to make a right triangle to help me think about this problem. And there's a couple of different ways of how you can think about it, but what I'm going to do is I'm going to make a right triangle to help me think about this problem. And there's a couple of different ways of how you can think about it, but what I'm going to do is I'm going to make a right triangle to help me think about this problem. So the way I think about it is, so arcsine, remember the idea of the inverse trig functions is they give you an angle. So arcsine of x gives us an angle theta, where sine of theta returns the value x. And then there's a restriction that the angle is also between pi over 2 and minus pi over 2. So if I just focus on data being in the first quadrant for now, I can maybe draw like a little picture of a right triangle with an angle theta in it. And then with sine theta being equal to x, if I think of it as being like x over 1, and then I also think of sine as being like opposite over hypotenuse, I could draw a right triangle and label the opposite edge as x and the hypotenuse as 1 to sort of describe or represent this equation. And then what I'm looking for is cosine of this angle. So I know that cosine should be the adjacent over the hypotenuse. And we can figure out the adjacent side by using the Pythagorean Theorem. So the adjacent squared plus x squared would need to be equal to 1. So if you minus the x squared over and then square root, you could get the adjacent has a length of square root 1 minus x squared. And then with that, cosine being the adjacent over the hypotenuse. So that would just be square root of 1 minus x squared over 1, okay? So therefore, like cosine of arcsine of x could actually be simplified as square root of 1 minus x squared. Okay, so that's kind of an example of maybe how to work with an expression like this. It can maybe help to draw like a right triangle in order to figure out like how to evaluate something like this, okay? But I'll go ahead and end the workshop at this point. So yeah, go ahead and leave us feedback if you have any. And if you guys have any questions, you can go ahead and ask them at this point as well.